Okay, so well and welcome to today's session. So last time we had already discussed the procedure on the applications of the influence line diagram when we have various loading such as concentrated load and uniformly distributed load. So before we are going to have exercises on that, let us have an exercise on a Mahler-Breslau. So these are problems on your previous quiz last time. So for the problem number 1, we have a simply supported beam, the following dimensions and locations of points A, B, C. The beam has a total length of 10 meters. So for the first requirement is to get the ILD for reaction at A. So we remove this pin connection here and let this move vertically upwards so that it will have an ILD allowing A to move vertically upwards by 1. Okay, so as simple as that. So that is for reaction at A. So for reaction at C, similarly we're going to remove this. Of course it will be rotated at point A. So this is pinned down, and if you're going to move this one upwards, it will have an influence line diagram with one here. Okay, so this is the ILD for the reaction at C. For shear at B, the rule is we cut this section and then take note of the location of your reactions. So we're gonna let the leftwards or the left portion to deflect downwards and the right portion to be deflecting upwards. So we should note that this will be labeled as L1 3 meters and L2 to be 3 meters. Say this is Y1 and that is Y2. So Y1 will just have to look at the base of the triangle of Y1, it is 3. So we just divide that by the sum of the true triangles, which is 7 plus 3. Therefore, your Y1 is 3 all over 10. 3 all over 10. And for Y2, this is simply equal to 7 all over 7 plus 3, which would be equal to 7 all over 10. And for the shear at that point, the absolute value of Y1 plus Y2 will just be equal to 1. And as we can see, it will yield to 1. Okay, y1 and y2 will yield to sum of 1. So that is for the shear at B. And for the moment at B, we'll just have to apply here pin connection and push this upwards. Okay, so if we're going to push that upwards, this will be the figure, and then we need to compute for the value of the delta. See, I'm gonna label that as y1, and y1 will just be equal to the product all over the sum. And what will be the product? So the product of L1 and L2. So again, we are going to label this as L1, and that will be our L2. So the product of L1 and L2 is 7 times 3 all over 7, or all over the sum, which is 7 plus 3. So basically, this is equal to 21 all over 10, or simply equal to 2.1. Okay, for the second problem, first, the reaction at A. So again, we will remove the roller here, and we'll allow it to move upwards by 1. And it will tend to rotate at C. So there will be no movement along this restrained portion CD. See, this is equal to 1. So that is for reaction at A. Okay, for reaction at D, we're going to allow vertical movement along D by 1. Of course, this will deform by 1 also. So the ILD will be like this. Okay, so that is 1. Okay, that is for the reaction at D. Okay, moving on to shear at B. So as for the shear at B, so this is B, we are going to cut this B and allow left portion to deflect downwards, and the upper portion deflect upwards. And again, this will be limited up to C because P has a hinge, and there will be no shear at along C and D. Okay, we just follow that on the bottom, on the left portion. So we label this as y1 and y2, and then take note of the distances. Say this is L1, which will be equal to 4. Okay, shear at B, or B is 4 meters from A, and the remaining dimension here will be equal to 2. Okay, totaling to 6. So we apply the general rule. Y2 is simply take a look at the base of the triangle involving y2, that is actually 4, and then divide it by the sum of the two triangles, is 4, plus 2. So therefore this is equal to 4 all over 6. And y1 will be equal to the base of the triangle involving y1, that is 2 all over 4 plus 2. So basically this is 2 all over 6. So observe that the sum, the absolute value of this y2 and y1 will just sum up to 1, okay? Because 4 plus 2 is 6 all over 6. So this is the ILD for the shear at B. So moving on to the moment at B, again we are going to apply here a hinge at B and move that upwards. So it will allow a deformation, okay, wherein the deformation is a common height to the triangle that will be formed from A to C. Say this is labeled as y1. So y1 is simply equal to the sum all over the product all over the sum. So this refers to L1 and L2. Say L1 is equal to 4 and L2 will be equal to 2. So the product is 4 times 2 all over the sum, which is 4 plus 2. So basically this is 8 all over 6. So y1 will be equal to 8 all over 6. Okay, that is for the moment at B. So moving on to the third problem. So reaction at B. First, you're going to allow this to move upwards by 1, and it will simply have, okay, an ILD equivalent to this. So this is a pin connection at C. Basically it will just be rotated at C. Say labeling the, say we label y1 and y2. So we'll just have to use the triangle. So y1 is 2, 7, and the y2 is 2, 5, and y2 is set to be 1. So therefore y1 is equal to 7 all over 5. So that would equate to 1.4 units. This is 1.4 and this is equal to 1. Okay, so next for the reaction at C. So for the reaction at C, I'm going to allow this to move upwards by 1 unit, and then project it all over the beam. So of course this will be rotating at B. Okay, so the ILD will look like this. So, say this is y1 equal to 1, and that will be equal to y2. So by ratio proportion, y1 is to 5 as to y2 is to 2. This is set to be equal to 1. So therefore 2 y2 is equal to 2 all over 5, which will yield to a value of 0.4. So next, shear 4 meters from E. Of course, we're gonna measure a point 4 meters from E. So let this be our 2 meters. And what is left here is 3 meters. So for shear at that point, we're gonna allow a downward movement here. Okay. So the position of the beam stays or pinned at B. And then an upward movement here. Okay, so this is the ILD. So we go for the ordinates. Say this is y1, y2, and that will be y3. So y1 is simply equal to, okay, look at the base, it is 2 over the sum of the two bases of the two triangles that are within the supports, okay, B to C, and that is 2 plus 3, it is equal to 5. So therefore y1 is 2 all over 5, which is equal to 0.4, and then y2 is equal to 3 all over 5, which is 0.6. Again, the sum will be equal to 1 for that. And then solving for the y3, or the third ordinate, we just utilize the similar triangle between y1 and y3. So we can just say that y3 is to 2 and y1 is to 2. So basically y1 will just be equal to y3, which is equal to 0.4. Okay, so that is the shear 4 meters from A. For the moment 4 meters from A, again we take note of the distances here. We consider this point and then move that upwards. So moving that upwards, the beam stays at the position at B. It will just rotate at B. Okay. And then it stays at C position. So this will now be our influence line diagram for the moment 4 meters from A. So let us label the ordinate here. Say this is y1 and that will be y2. So y1 will be equal to the product all over the sum. So the product is 2 times 3. Actually, that is the product of L1 and L2. And L1 and L2 are those distances that is within the boundary of two support reactions. So 2 times 3, and this is 2 plus 3. So this is 6 all over 5. So y1 will be equal to 1.2. And then we apply ratio and proportion between triangles involving y1 and y2. So the base of y1 is 2, is to y2 is to 2. And therefore, y1 will just be equal to y2, which is equal to 1.2. Okay, so that's it for this problem. Moving on to the next problem. For reaction at B, we allow this one to move upwards by 1 unit, and this is projected here, which extends on the overhang. Okay, so this is the influence line. See, this is y1, y2 equivalent to 1. See, this is y3. So you just have to utilize similar triangles. y1 is to 7, y2 is to 5, which is also equal to y3 is to 1.8. Now this is set to be equal to 1, therefore we can just pair that into y1 and y3. So pairing that by y1, you just cross multiply 7 here, therefore 7 times 1 all over 5. So y1 is 7/5, which is equal to 1.4. And then y3 will also be paired to this side of the equation. So we have 1.8 by 1 all over 5. So we have y3 equal to 0.36. So that is for reaction at B. Moving on to the reaction at C, we allow vertical movement at C by 1, and then extend that beam rotating at B T, which will be also parallel to the overhang. Okay, so we label the coordinates. So this is y1, this is y2 set to be equal to 1, and then this is y3. So again, we proportion it. y1 is to 6.8 as 2, y2 is to 5 is to y3 is to 2. So this is set to be equal to 1. So therefore y1 is 6.8 divided by 5. That would yield to 1.36. And then y3 will be as well paired to this side of the equation. So 2 will just be cross multiplied to 1 divided by 5. So 2 all over 5. That is equal to 0.4. Okay, so that is for the reaction at C. And then moving on, the shear 1 meter from A. Okay, we just have to bisect or consider a point here. And we let that to move. But this one is a different scenario because we have here an overhang, or in short, this portion is not enclosed by two support reaction. So basically, we do not treat this as applying the rule that this is going downwards and then this is upwards. Okay, and we have no way how to deal with this because two support reactions are present on the right portion. So when we have an overhang, we'll just have to let that shear to go up, because if we can see here, if we apply a unit load from left to right starting at this point, so this is the unit load 1, of course we cut that one and consider the left portion, say this is the cut section. So 1 here will still be present until it will move on the right portion, okay, or it will move 1 plus. See, this boundary is 1 minus, so 1 will move eventually to 1 plus, or it will leave the cut portion. So remember that our shear will just be equal to the summation forces vertical, and if our unit load is within the boundary of 1 minus, then 1 will still be present on this cut portion. However, it will exceed beyond 1 minus, 1 will be no longer present on this cut portion. So there will be no shear at all on the right portion of this point. See, this is A prime. So just right of A prime, there will be no value or zero value. So just left of A, our shear will be equal to 1, and will yield to 0 just right of A prime. So we have here a value equal to 1. Okay, so that is for the shear 1 meter from A, and that is an overhang. Take note of that. Okay, so moving on to our moment 4 meters from A. Again, we're gonna measure that location and consider this point. So we allow that to move upwards. Okay. and we have an overhang on the other side. So notice that your beam will just have to rotate along your support reactions. See, we label all the dimensions. See, this is y1, y2, and y3. So our L1 here is 2 meters and L2 is 3 meters, following your criteria. The location 4 meters from A. So therefore, we first compute the delta that is within the enclosed boundary of the two support reactions. So this is product of L1 and L2 all over its sum. So therefore, this is 2 times 3 all over 2 plus 3. So therefore, this is 6 all over 5. And y1 will be equal to 1.2. So we now employ ratio and proportion. For this right portion, we have y1 is to 3 is to y3 is to 1.8. And then you can see also that y1 is to 2 for this other side, okay, which is y2 is to 2. So therefore, y1 will just be equal to y2, which is 1.2. So for y3, we'll just have to cross multiply 1.8 to that, multiplied by y1, which is 1.2, divided by 3. And that will be equal to 0.72. Okay, so moving on, we have this frame. So for the reaction at A, we'll just have to treat this as a beam, because we are just considering a unit load, vertical unit load. So it will be treated as a beam. Say from A, just have to move it by a single unit, and it will be restrained along D, A, so there will be a vertical movement on the overhang as well as along D. So this will be the influence line diagram for reaction at A. So we just have to compute for its coordinates. Say this is y2, y1, and y3. So remember that y2 is equal to 1. So that by ratio and proportion, y1 is to 6.5 as to y2 is to 4 as to y3 3 is to 2.2. So this is equal to 1, and then y1 will be equal to 6.5 all over 4, and y3 will be paired to this, 2.2 times 1 all over 4. So we have the values. Okay, so that is for the reaction at A. Now moving on to the reaction or the shear 1 meter from C. See, this is the point. We take note that this is equal to 1 meter, and the remaining dimension that was enclosed by the other support reaction is 3 meters. So apply the rule. We're gonna let that to deflect downwards. Okay, it will strain at point C, and this as well will tend to move upwards, will restrain at D, and extended at E. Okay, so we label the coordinates. Say this is y1, y2, y3, and y4. So we first compute for y1. We look at the base of the triangle of y1, that is 1, divided by the sum of 1 and 3. So that is equal to 1 all over 4, or 0.25. And then y2 is, the base of y2 is 3 all over the sum 1 plus 3, or that is equal to 3/4. That will be equal to 0.75. So notice that it will again yield to 1. We will sum up to 1. And then by that, you can already use this y2 in solving y4 and y1 in solving y3 by ratio and proportion again. Let us have the right portion. Say y2 is to 3 is equal to y4 is to 2.2. So get the value of y2, which is 0.75. So therefore y4 is 0.55. So we do the same on the left portion involving y3. So y1 1 is to y3 is to 2.5. So we get the value of y1 0.25. So therefore y3 is equal to 2.5 times 0.25. So this is y3.625 for y3. Okay, so that is for the second requirement. So for the third requirement, moment 3 meters from A. So if this is A, I'm gonna measure here 3 meters dimension from A. So this is the point. So this is 3 meters. So the remaining dimension here is 1 meter. and we're going to allow that to deflect by unit deformation here. Okay, so we still need to compute that and project it up to B and up to E as well. Okay, so we label y1, y2, and y3. So computing for y1, that is the product all over the sum. So that is 3 times 1 all over 3 plus 1. So basically that is 3 all over 4, or equal to 0.75. So solving for y2, let us consider this triangle. y1 is to 3 as to y2 is to 2.5. So we consider y1 to be equal to 0.75. Then we have that to be equal to 0.625. Similarly, we use similar triangles on y1 and y3. y1 is to 1 as to y3 is to 2.2. So we substitute the value. By cross multiplication, we have y3 75% of 2.2, which is 1.65. Okay, so we are done with the ordinates and ILD for the third requirement. Okay, so lastly, we have moment 7 meters from A. So this is A, 7 meters. So 7 meters exceeds this portion. So basically, I think we have a clerical error that this should be 7 meters from B. So we measure 7 meters from B. So it will exceed D eventually, because from B to D, that is 6.5, we still have to extend it by 0.5 from D. Say that is 0.5. So it so happened that the location of 7 meters from B will extend from D at 0.5 meters. So if this is the case, we are dealing with an overhang. So for an overhang, of course, the left portion will have both reactions. Okay. So usually, if we apply the Mahler-Breslau, it is enclosed between two, or the location is enclosed between two support reaction, but this time the reaction lies on one side only, so we cannot really apply that Mahler-Breslau. So we have no choice but to apply equilibrium equation to solve for the moment at this point. Okay, so if you're going to treat this as a beam, of course we treat this as a beam. Say we have an overhang here, and say this is a roller support, and a pin connection here. So let us cut a portion and consider the left. So note that we will be needing here RE and RF. So we allow a unit load that is changing, that has changing location, starting from left to right. Say this cut portion here is defined as 7 meters. Okay, so we form an equation out of this. Say mx is just the moments wherein positive, concave upwards, and negative, concave downwards. So we consider first the unit load. So we take moments at this point. So that is a concave downward effect. So we have negative 1 times the moment arm 7 minus x. Okay. So if that is, this is x, this is 7 minus x, of course. And then RE, we have a distance of 7 minus 2.5, and that is equivalent to 4.5. And then we add RF. So RF is this. We have moment arm of 0.5. So basically this will be our moment equation. So your moment equation includes the value for RF and RA as well. So we will be needing the influence line diagram for RA and RF. So illustrating our ILD for RA. See, this is for RA. We have to allow movement at A. Of course, that is restrained along F. See, that is the diagram. Okay, we'll be needing the value of our ordinate 0.5 from D. So this is 0.5, this is 4, and this is 2.5. So the ordinate of this one is 1. So I'll just label this as y1 and y2. So y1 is 2, using this triangle, 6.5 as to 1:4. So therefore, y1 is 6.5 divided by 4, that is equal to 1.625. And for say y3, we have ratio portion 1:4 is 1 is equal to y3 is to 0.5. So y3 is 0.5 divided by 4, that is 0.125. Okay. So if you need y2, y2 is 2.2 as 1:4. So therefore, y2 is 2.2 all over 4. That is equivalent to 0.55. So we have a complete coordinates, or we have just computed what we needed on influence line diagram for RE. So of course, we establish also our ILD for RF. Again, we drew the line here. So we have to allow a 1 unit deformation along F. So this is pinned at this point. So we draw it this way. So this is restrained at this point, so it will just have to rotate at point E. Say this ordinate is equal to 1. We'll be needing this ordinate, of course. .5 meters from D. Okay, from D, this one. Say this is y1, y2, and y3. So we just placed the distances for our reference. Actually, this is 2.2. So here we have y1 is to 6.2 is equal to 1:4. So therefore y1 is equal to 1.55 or 6.2 all over 4. So for y2, so y2 is to 4.5. Okay, so this one, that is 4.5 as 2, 1 is to 4. So therefore, y2 is 4.5 divided by 4. That is 1.125. And then for y3, just have to utilize this one. We have y3 is 2. 2.5 as 2, 1 is to 4. So 2.5 all over 4 is 0.625. Okay, so we will be using that in tabulating this equation. So what you do is to enter this in your calculator and then just change the values. Say let us have a matrix having x as the first column. Then we have RE, RF, and MX. Okay. So we say here that when x is 0, what is RE? When x is 0, we locate this one. So we look at the coordinate of this. What is that? Y1. Y1 is 1.625. So we place it here. And then RF is equal to y3, 0.625. Okay, so we enter this into our calculus. Then we have a value of the moment equal to 0.625. Next, so let us have to move our unit load 2.5 meters from point B. So 2.5 meters from point B, again, we refer to the ILD of RE. So as we can see here, that RE will just be equal to 1. Okay. And your RF will be equal to 0. So calculating your MX out of RE and RF with X is equal to 2.5, we have MX to be equal to 0. So next we are going to transfer our unit load on D. Okay. So transferring our unit load on D, this is the unit load. That would yield to 6.5, a distance 6.5 from B, so that our RE, how much is RE? Is 0. Here it is, the value is 0. And for RB or RF, our value is equal to 1. So we calculate, then we yield to a moment of 0. Okay, so we now move to 7 minus, meaning this is just left of this point. Say this point is G. Okay, just left of G, still your 1 will be present along the cut section on the left portion. So what will be the value of RA? So your RA is Y3 here, Y3 equal to 0.125, and your RF is Y2, 1.125. 0.125, then we calculate, then we have a value of 1.125 for that. And then moving our unit load just right of G here, okay, 1 will no longer be present on the cut section, therefore there will be no value for RA, and reaction at F. Take note of that. So there will be no 1 here. So basically, all of the values will remain to be 0. Okay. So these are now our values for the influence line diagram. So let us graph that one. Say this is our beam. We have a support here, and support here. Okay. So when x is 0, our moment is 0.625. That is a positive 625. And then when x is 2.5, we'll have a value of 0. Okay. So when x is 6.5, actually this is 2.5. This is 4. And 2.2. So when x is 2.5, our value is equal to 0. When x is 6.5, our value is also 0. 7 minus that is 1.125. So we're gonna measure here, see, this is 0.5, so it will have a value of 1.125. And it is 0 at this point. And then it will have no value at this point. So this will be the moment influence line diagram for the moment at 7 meters from B. Okay, so Please stand by for the next video on the application of the ILD, wherein we're gonna apply various loading.